4.3 Modern Atomic Theory. Key ideas. What is the modern model of the atom? How are the energy levels of an atom filled? What makes an electron jump to a new energy level? In the modern atomic model, electrons can be found only in certain energy levels, not between levels. Furthermore, the location of electrons cannot be predicted precisely. Electron location is limited to energy levels. In Bohr's model, electrons can only be in certain energy levels. They can gain energy to move to a higher energy level, or lose energy to move to a lower energy level. So here I'm going to show you what that means. So this is an example of a nucleus. We're going to draw a quick atom. And so we have energy levels. So we've got first ring, second ring, third ring. And so electrons are going to exist only on these blue rings. Now, generally they want to be in what is called the ground state, or the normal state of their energy. So if the ground state of an electron is to exist on this first energy level, they would like to stay there. And so that's just like their regular everyday life. But if they gain energy, maybe like from light, and so maybe they're gaining energy for whatever reason, electricity, light, whatever, they can jump out to a different ring. And so if they then move out to these more excited, or these higher energy rings, then they have more energy. They can then, again, because they like to stay in their regular everyday life ground state, they can then fall back down and lose the energy and go back to their regular home. So in chemistry, we like to say that electrons can act like waves, and so things that travel through waves would be like light, radio waves, and things like that. So electrons can act like waves for some reasons, and for that reason, the exact location of an electron cannot be determined. So we can never know the exact place an electron is located at a certain point in time. However, an orbital is a region in an atom where there is a high probability of finding electrons, so where they're usually located. The number of energy levels that an atom has depends on the number of electrons in the atom. The valence electron is an electron that is found in the outermost shell of an atom, and that determines the atom's chemical properties. So later on, when we're talking about in the next chapter how atoms bond together, the valence electron is the most important part for that particular factor. So we said an orbital is where electrons are likely to be found. There are 4 types of orbitals. And just know that there are different types of orbitals. We're not going to get into a whole lot about that, but just to introduce you to the idea, there are s, p, d, and f orbitals. Each orbital can hold 2 electrons. So think about an orbital like a shoebox. Shoeboxes hold 2 pairs of shoes. But then you may have a large amount of shoeboxes in your closet. So an orbital holds 2 electrons, but there may be a large number of orbitals in the atom. Orbitals determine the number of electrons that each level can hold. So these levels are the rings that we were showing in the previous slides. And so in the first energy level, you can have one s orbital, and that one s orbital holds 2 electrons. So the first ring holds 2 electrons. Energy level 2 has one s, and 3 p orbitals. And so the second energy level can hold up to 8 electrons. And so each orbital can hold 2. If we have one s and 3 p orbitals, that's 4 total orbitals, and that makes 8 electrons. Now I'm running out of space. I won't be able to draw the rest, but the third ring can hold, it has 1s, 3p, and 5d orbitals, so it can hold 18 electrons. And then the last final ring, energy level 4, has 1s, 3p, 5d, and 7f orbitals, so it can hold up to 32 electrons. So a little bit ago we said that electrons can jump between energy levels when they gain or lose energy, and so generally that is going to be that they gain or lose energy in the form of light. So when they absorb light, they get excited and gain energy, and when they give off light, they are releasing that energy. So the lowest state of energy an electron can have is called the ground state, and again, that's like its home. That's where it likes to be, just normal every day. Then if an electron gains energy by absorbing a photon or a quantum of light, it moves to an excited state. So whenever you gain energy, maybe you drink an energy drink or you eat some food that gives you energy, then you become excited or hyper, you have more energy. So for electrons, they gain or lose energy by absorbing a photon, and a photon is a unit or quantum of light. The electron then can release a photon and fall back to a lower level. And so just like when we maybe have energy drink or drink something with caffeine or whatever, we gain that energy, but eventually we're going to use it all up and we're going to fall back down and go back to our regular ground state of being tired. Same with electrons. They can release a photon and fall back to the lower energy level. And so what that means is that electrons can release light, and so they can give off light. Photons have different energies. The energy of a photon corresponds to the size of the electron jump. So if the electron is jumping just one ring, then that photon is going to have a certain amount of energy. But if the electron is jumping 2 rings, it will have more energy. And so atoms absorb or emit light at certain wavelengths. Each element has a unique atomic structure, and therefore the wavelengths that they emit depend on the particular element. So wavelengths are a type of atomic fingerprint that can be used to identify a substance. So scientists can look at the wavelengths of light that are being emitted by the electrons after they've been excited and they're losing or giving off that energy. They can look at the wavelengths of light that are being given off and determine what the element is. This is one way that scientists know what stars are made of. They can compare the wavelengths of light given off by certain stars to the wavelengths of what we know that those particular elements give off here on Earth, and compare and determine what is making up the star.